So having seen tries, we're now ready to talk about suffix tries, which will be the first actual proposed suffix index data structure that we might want to use. Okay, so what's a suffix trie? Well, a suffix trie is a trie consisting of all the suffixes of a text T. All the suffixes, right? So like the suffix that's the whole text, the suffix that's the whole text except for the first character, the whole text except for the first two characters, and so on, right? So it's a trie containing all those suffixes. And you may be saying to yourself, wait a minute, that sounds like a lot of stuff to put into a trie, right? Because the text might be relatively long, and therefore many of the suffixes of the text will also be long. So just to sort of see this pictorially, let's look at a text together with all its suffixes. I'll have more to say in just one moment about this $sign, funny little $sign thing that you see at the end there. Just ignore that for now. But here's a picture of a text and all its suffixes, right? So the suffix consisting of the entire text, the text missing its first character, missing its first two, first three, first four. So that's all of them. Okay? And obviously, if you have all of the suffixes of your text and then you just go to count up how many characters that is, it's a lot of characters. It's growing not linearly with the number of characters in the text T. Let's say the number of characters in the text T is m, lowercase m. It's growing with m squared, roughly speaking. Really, it's m times m plus 1 over 2. In other words, if you see this red part as being sort of like half a rectangle, right, or half a square almost, it's sort of like half an m squared square, right? But it's still growing quadratically, even though it's only half the square. Okay, so it's growing with m squared. So if you are naive in how you represent all the suffixes in the data structure, you are potentially paying a big price, a price that is quadratic in the number of characters in the text T. And this is not a small problem. This is a serious problem, which we will address. But for now, we can retain at least some hope because after all, like we said before, the trie is not naively representing all the strings in the collection. It's doing this prefix sharing thing, right? So it's doing some elimination of redundant paths by combining the paths belonging to common prefixes. Okay, so maybe that does something for us. Okay, now let me explain what this funny $sign character is all about. As we start to look into these suffix-based indexes, it's going to be convenient, and we'll see a couple reasons today why it's convenient, to add a special extra character on the end that we represent using $sign. There's nothing special about $sign in particular. It's just a character that we pick because it's unlikely to be elsewhere in the string, and it's just a convention to use $sign. It has a special name. It's called the terminator. So the $sign character is a terminator character, terminal character. And what's its function? Well, its basic function, and the $sign character is a character that does not appear elsewhere in T. And, importantly, it's defined so that in alphabetical order, it always comes first. It comes before all the other characters in the alphabet. So this $sign is alphabetically before, say, A in the DNA alphabet. What is the function of this $sign? We'll have a couple different things to say about what exactly its function is, because it has one function in terms of the shape of the tree, and we'll talk about that later. But intuitively, you can think of its function as enforcing a rule that we all know, but that we treat as kind of like a special case rule. Right? The rule is that if you're looking for words in dictionary order, in alphabetical order, and you need to figure out which word comes first, as or ash, as being a prefix of ash, right? So you're comparing two words, but one of them is a prefix of the other. We know that the rule says that the prefix comes first. The prefix, the shorter one that's a prefix of the other, comes before the other in alphabetical order, in dictionary order. Okay? So by adding the $sign, in a way, what we're doing is obviating the need, taking away the need to have a special rule. We don't need a special rule anymore because by the time we get to the $sign, the tie is broken, right? So if I take as and ash, then if I want to know their relative order, I have to apply the rule. Oh, this is a prefix of that, so it comes first. However, if I stick this $sign in, remember the $sign is different from all the other characters in the string, I don't need a special rule because by the time I get to here, the tie is broken and we know that as comes before ash. So intuitively, that's the purpose that it serves. It's so that we don't need a special case, an extra rule, for the case where one string is a prefix of another. Okay. All right. So let's say I start with a string. Let's take a nice small one because it's actually going to take a little time to draw the entire trie, and it takes too long if the string is too long. So let's start with a small string. Let's add that $sign like we said we always need to do. So the string that we're going to put into this trie is ABA $sign. Okay, and so now our job is let's put in all the suffixes. Okay. So let's start with the suffix that's the whole string. Okay, that's the first one, the suffix of ABA $. Okay, so let's put that one in. And I'll just draw it like this. A. This is kind of familiar. It's what we did before when we built the trie over those strings like instant and internal and all that. ABA and then $sign. There we go. So there's one of the strings that we're going to add to our trie. It's the suffix that is the entire string. Okay, so now let's go to the next longer suffix. That's the one that's just BA $sign. Okay, BA $sign. So let's do that one. Okay, so coming off the root, we need a new edge because this new suffix starts with B. So here we go. Here's B A $sign. Okay, great. So that was the second longest suffix. Third longest suffix is just A $sign. And oh look, we already have an A outgoing edge from the root, so we're not going to add another path labeled A leaving the root. We don't do that. Tries are the smallest tree such that all the keys are spelled out. So we're going to collapse the shared prefix, and instead we'll just draw the $sign as sort of coming off of this node. There we go. All right, and there's one more suffix to deal with, which is just the $sign, right? Okay, and so that's just going to be one more edge coming off the root, and it's labeled $sign. Okay, so there it is. There's our suffix trie. There's a nicer picture of that same suffix trie. So we took all the suffixes of our string and we added them to the trie. The collection of keys that this trie is holding is just all possible suffixes of our text. Okay. So let's show a larger suffix trie. I don't want to write it out by hand, so let me just show it to you. Here's a slightly longer text, ABA, ABA. We always have to put the $sign on the end. And let's take a look at the suffix trie for that string. Okay, obviously this is bigger. But we can see that suffix trie has the property that we expect any trie to have, which is that each of the keys is spelled out along some path from the root going down. Okay, so for example, the longest and the shortest suffixes are clearly both here, right? The longest suffix is the one that consists of the entire string. If we start at the root, we should see it spelled out. A-B-A-A-B-A $sign. Okay, and there it is. A-B-A-A-B-A $sign. So there's the longest suffix. And then the shortest suffix is the one, the sort of trivial one that just consists of $sign, and there's that, right? So we can see it right there. Okay? So, what we can say about the suffix trie is that each path from the root to a leaf represents a suffix. And, going the other way now, each suffix of T is represented by some path from the root to a leaf. Right? This is a kind of one-to-one relationship. Each suffix corresponds to a root-to-leaf path. Each root-to-leaf path corresponds to a suffix. Something important I want to emphasize is that we are talking about root to leaf paths, not just any path, right? Not just a path that might end anywhere in the trie, but we're talking specifically about root to leaf paths. So in other words, there's something special about the leaves that helps us to have this one-to-one relationship. Okay, so I'm going to argue that this is actually one of the things that the $ has done for us, right? The addition of the $, the terminator character on the end of the string, is what allows this property to hold, this one-to-one mapping property. So, more specifically, would this property, this, again, one-to-one mapping property between suffixes and root to leaf paths, would that still be the case if we didn't use the $? And so here we go. Let's get rid of that final trailing $. It's now gone from the string t. And let's look over here. Here's a version of the suffix trie, but again, where we've got rid of the trailing $, you can see now this is a different trie, right? If I switch back and forth between the old one here and the new one here, you can see some stuff has gone away, right? Because we got rid of those nodes that had $ as their incoming edge. And now what we see is that each path from root to leaf represents a suffix. That first part is still true, right? This is still true. But the second part of each suffix is represented by some path from root to leaf is no longer true, because let's take a suffix, for example, of just BA, for example. And so if we walk down from the root, we follow these two edges, and we're not in a leaf, right? We're just in one of the internal nodes, right? So BA is a suffix, but that path that when we walk down from the root, according to the characters B and A, doesn't end in a leaf. So the lesson here is that we need the $ on the end of the text t in order to have this property, this bijective one-to-one mapping property that each path from the root represents a suffix. Each suffix is represented by some path from root to leaf. Okay, so great. That's another thing that $ is doing for us. A quick bit of sort of vocabulary before moving on is we can think of nodes in this trie as having a label, right? Obviously the edges have labels, and the edge labels are characters, but we can also think of the nodes as having labels, where the label of a node is the string that would be spelled out on the edge labels if you walked from the root to that node. So for example, if we look at this node right here, pointed to by that blue arrow, okay, well, what's the label of this node? Well, it's the string that would be spelled out if I started here and walked to that node and read off the edge labels. So in this case, that would be BAA. So the label for that node would be BAA. Okay, so these aren't explicit labels. We're not actually storing them in the data structure, as a practical matter. They're more conceptual, right? The label of a node is this idea of the string that's spelled out as we walk there from the root. Okay, so now that we have our suffix trie data structure, here it is, we'd like to be able to query it, right? So back when we talked about the trie data structure, we would query it with things that might be keys, things that might be in the collection or that might be in the associative data structure represented by the trie. Here with the suffix trie, we want to ask a slightly different kind of question. We want to ask a substring query. We want to know whether our pattern S is a substring of the text T. And what we have available for us to use is a suffix trie. So a trie that's built over all the suffixes of the text T. So on the one hand, we're looking for a substring. On the other hand, the things that are in the data structure are suffixes. But this is okay. Why is it okay? It's okay because a substring of the text T, right, which is sort of represented here by this blue box in the middle of the longer gray box. Imagine the gray box is T and that blue box is a substring of T. A substring is a prefix of a suffix of T. All right, so looking down here, this purple box is a prefix of this longer suffix of t. Right? So imagine this is just a suffix of t, and here's a prefix of a suffix, and of course that corresponds to the substring that you see depicted just above. In fact, we could have flipped this around, right? It's also correct to say that a substring is a suffix of a prefix. But because what we have in our data structure is a bunch of suffixes, it's more appropriate to describe it this way, right? A substring of the text t is a prefix of some suffix of the text t. And all the suffixes are here in our suffix trie. So each of the substrings must also be here, right? Each of t's substrings is a prefix of a suffix. And so each of t's substrings is spelled out along a path starting from the root, right? So any substring you care to pick of t, it is spelled out along some path starting at the root. Because, why is that? Well, because we've got all the suffixes in here, and a substring is just a prefix of a suffix. So it must be along one of those paths. Okay, so let's take as an example a simple query string of BAA. We would like to answer the question, is BAA a substring of t? So what do? We start at the root, and we walk down according to the characters of our query. Again, I'm using this term walk down. It just means that at each step, we're taking the next character from our query. We're asking whether there is an edge to a child labeled with that character, and if so, we follow the edge. And if not, we fall off the trie. Okay, in this example, that means we'll start at the root. We'll follow edges labeled BAA. BAA, that takes us here. Because we got there without falling off the trie, we know that the answer to the query is yes, right? In other words, BAA is a prefix of a suffix of t, thus BAA is a substring of t. So in general, the algorithm that we'll use to check whether some string s is a substring of t is we'll start at the root, we'll follow edges labeled with the characters of s, that is, we'll walk down according to the characters of s. If we fall off, then the answer is no, right? Because if we fall off, what that means is there is no substring that has our query string s as a prefix. Therefore, s does not occur as a substring of t. So if we fall off, the answer is no, s is not a substring. On the other hand, if we don't fall off, if we exhaust all the characters of s and we end up still standing somewhere on the trie at the end of that, then s is a substring of t, because s is a prefix of a suffix of t. Just as we said when we discussed the trie, we said, you know, for a reasonable representation of this trie data structure, it should be possible to follow one step of this procedure, stepping from a parent node to the appropriate child node using the next character from our query as the key. It should be possible to do one of those steps in constant time. If we use, for example, hash tables to represent the parent-child relationships, then maybe it's constant expected time. But we don't have to. We could use a lookup table or something else like that. And it's reasonable to suppose that one of those steps is constant time, in which case this overall process, since we have to do this at most once per character of the query, this overall process is a big O of n time query, where n is the length of our query string s. Okay? Okay, here's a different kind of query that maybe we can still find a way to answer with the suffix trie, but it's not a simple substring query, a presence or absence substring query. It's a counting substring query. So this time we'd like to know the number of times that a string s occurs as a substring of t. Not just yes or no, but how many times. Okay, well, still we can fall back on our knowledge of what the suffix trie is, what it means. And we recall that the suffix trie represents all the suffixes of the text t. So let's say we start, as we usually do, by starting at the root and walking down according to the characters of our query. Right, our query is AB, so that'll take us here. Okay, and let's let n, small n, be a name for the node that we reach after walking down according to our query. So that's this node in this example. Okay, so the next point I'm going to make has to do with the subtree of the trie rooted at n. All right, the subtree of the trie rooted at n, in other words, this subtree down here that I've drawn a sort of orange line around, that's the subtree that holds suffixes for which s is a prefix. Right? These are, down here is the part of the trie containing only those suffixes that have s as a prefix. Really the suffixes also go all the way back up to the root. So in a way, I'm just looking at suffixes of those suffixes. But at any rate, the important thing to notice about this subtree is that the leaves in that subtree correspond to the suffixes that have s as a prefix. I'll say that again. The leaves of the subtree, there's two leaves, the leaves of the subtree correspond to the suffixes for which s is a prefix. Because there are two such leaves in the subtree, right? In the subtree with the orange line around it, there are two leaves. That means there are two suffixes for which s is a prefix. In other words, the answer to the query, what's the number of times that the string s occurs as a substring of t, is 2. Okay, so not only were we able to answer the presence-absence question, right, just the mere fact that we were able to walk down according to the characters of our query without falling off told us that it must occur at least once, but more than that, by looking below the point that we finished our walk down and asking how many leaves are there in that subtree, we were able to additionally answer this question of what number of times does the query occur. Okay, so in general, if we want to answer this query, we walk down according to the characters of our query s. So walk down according to s. If we fall off, then the answer is no, right? Falling off means there is no suffix for which our query is a prefix. So in that case, the number of times that the string occurs is 0. If, however, we don't fall off, we end up at some node n, then the answer is the number of leaves in the subtree rooted at n. And we can find, for example, here's another example with n and the orange box and the red nodes labeled as if our query was just the letter A. The leaves can be counted by performing a depth-first traversal of this subtree. Really any kind of traversal, but for simplicity, let's just say we're doing a depth-first traversal of that subtree, right? So we would sort of go down here, see a leaf, go down here, see a leaf, pop back up, go down here, see a leaf, pop back up, go here, see a leaf. Every time we see a leaf, we increment a counter. Okay? So we looked at a presence-absence query for which we have a query string. We looked at this query where we count the number of times we see the query. Here's another question we can ask, and this time there's no query string. Right? We're just asking a question about t, about the text t itself, and trying to see if, by looking at the structure of the suffix trie, can we answer this question. And the question is, what's the longest repeated substring of t? In other words, what's the longest substring of t that occurs at least twice in t? Okay. All right. Well, again, let's fall back on our knowledge of what the suffix trie represents. Right, the suffix trie represents all the suffixes of the string t. So if there is a repeated substring, then it must be a common prefix between two of the suffixes, right? Any repeated string is a common prefix between more than one suffix. So in some sense, what we're asking here is, what's the longest common prefix that we observe between any pair of suffixes? Okay? And I'm going to argue that the way we know what's the longest common prefix between any pair of suffixes is we can look at this trie, we look at the nodes that have more than one leaf underneath them, right? Because that means there's more than one suffix that has the node label as a prefix, right? And we identify the deepest such node, right? Deepest meaning farthest from the root. So we're trying to find in the trie what's the deepest node that has more than one leaf in the subtree underneath. And we can see by looking at this picture what node that is, right? It must be this one, right? That node is at depth 3, right? It's 3 levels down from the root, and it has more than one leaf underneath it. And that's not true of any of the nodes at level 4 or level 5 or level 6 or level 7, right? This is the deepest one. Okay? So the longest repeated substring corresponds to the label of this node, which is ABA. Right? Recall that our string is ABA dollar, right? That's our text T, right? So that answer would seem to be correct, right? ABA is the longest repeated substring in that text. The way we can find that is we can look at the trie and find the deepest node that has more than one child, which in this case is that node, and those are the 2 children that it has. So having established how we query this data structure, in the next video we'll look at a few statements regarding its size, how many nodes and edges it has.